Hello, sir. Good afternoon, sir. Gangadhar Bhatt, sir.
Hello, sir.
Uh,
Hello,
can
sir.
you hear me, sir?
Hello, sir. Can you hear me, sir?
Yeah, I can hear you, sir.
Okay, sir. Okay.
Can you share the slide, sir, just to check your video and PPT sharing?
Whether I have to share that, let us see. Wait for 1 minute.
Okay, sir. Okay, sir.
ಇದೆಲ್ಲ ಅಪ್ಲೈ ಕಡಪುಡು ಅಂತೆಲ್ಲ ಇದ್ದಿತ್ತು ನೀವು ಶೇರ್ ಅಂತ
Yes, sir. Your desktop is visible, sir.
ಕಂಟ್ರೋಲ್ ಎಂಡ್ ಮತ್ತೆ ಎಂಡ್ ಪಪ್ಪೋಡು ಒಂದಿನಿ Hello?
Sir.
Hello, sir. Can you hear me?
Yes, sir. Yes, sir. Very clear.
I have shared my PPT.
Yes, sir. It is visible, sir.
Okay, sir. Thank you, sir.
Okay. We will start at sharp at 2 o'clock, sir.
Okay,
you
sir.
can, join at 1:55.
Okay. Your good name?
Hafiz, sir.
Hafiz. Okay, thank you.
Okay, sir.
Yes. Hello, sir. Sir. Gangadhar Bhatt, sir.
Hello, madam. Dr. Sharmila, madam. Hello, madam. Hello, madam. ಇದು ಕೇಳ್ತದೆ ಮ್ಯೂಟ್ ಅಲ್ಲಿ ಇದೆಯಾ ಇಲ್ಲ ಆಚೆ ಈಚೆ ಏನು ಹೇಳ್ತಾ ಇದ್ದಾರೆ ಕೇಳ್ತಾ ಇಲ್ಲ ಹಲೋ ಮೇಡಮ್
Hello, sir. Good
ಹಲೋ
afternoon.
ಮೇಡಮ್ ಕ್ಯಾನ್ ಯು ಹಿಯರ್ ಮೀ ಮೇಡಮ್
Yes, yes, yes.
ಓಕೆ ಮೇಡಮ್
Shall we start, sir?
ಓಕೆ ಮೇಡಮ್ ಓಕೆ
Okay, okay. One second. ನಮ್ಮ ಇವರು ಇಂಟ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ತಾರೆ ಸರ್ ಕೋಆರ್ಡಿನೇಟರ್.
ಸರಿ ಮೇಡಮ್ ಆಗ್ಬೋದು ನನಗೆ ನಿಮ್ಮ ಹೆಸರು ಬಿಟ್ರೆ ಬೇರೆಯವ್ರದ್ದು ಯಾರ್ದಲ್ಲಿ ಗೊತ್ತಿಲ್ಲ ಮೇಡಮ್ ನಾನು ಜಸ್ಟ್
Good afternoon, sir. Good afternoon, everyone. A hearty welcome to you all for the second session of day 4 of the AICTE sponsored STTP on machine learning for societal applications. I, Professor Ankita, Department of Computer Science and Engineering, PA College of Engineering, take it as my honor in introducing the speaker of today's session, Dr. H. Gangadhar Bhatt, Professor, Department of Geoinformatics, Mangalore University, who will be delivering a talk on Geographic Information System for Visual Data Analytics. Dr. H. Gangadhar Bhatt served as a chairman in Department of Marine Geology during 2018-2019 and coordinator of Geoinformatics, Department of Marine Geology. His areas of specialization are geology, geomorphology, remote sensing (GIS), and satellite oceanography. Sir has guided 10 PhD students successfully and 8 students are working for their PhD. He has more than 60 research papers published in the national and international journals. He completed 4 research projects funded by Indian Space Research Organization, Ministry of Environment and Forest, Naval Research Board, and Ministry of Earth Sciences. He was awarded Indian National Science Academy Fellowship during 2002-2003. Sir is a life member of Geological Society of India, Indian Society of Remote Sensing, and Indian Society of Geomatics. He served as a chairman in Indian Society of Geomatics Mangalore chapter, and Sir has visited International Institute for Aerospace and Remote Sensing, Netherlands during 2001. He has wrote number of popular articles in Kannada newspaper on remote sensing and its applications. Sir has written a book in Kannada on ದೂರ ಸಂವೇದನೆ ಮತ್ತು ಅದರ ಅನ್ವಯಿಕತೆ. with this brief introduction, I wholeheartedly welcome Dr. H. Gangadhar Bhatt to this session. I kindly request you, sir, to take over the session.
Hello.
Hello.
Hello, madam.
So, welcome, sir.
Okay. Thank you, Ankita, madam, for your kind words.
Thank you, sir.
So, respected Dr. Sharmila, madam, Professor of Computer Science, then staff members of other departments, my dear friends. So, good afternoon to everybody. So, title of my talk is slightly different than what has been listed in the schedule. So, I will share my slides now. So, good afternoon to everybody once again. So, I will be speaking for another 2 hours on remote sensing data and overview. So, of course, when we talk about GIS, Geographical Information System, in fact, my original title was GIS for Visual Data Analytics. In fact, GIS comprises of remote sensing, GPS, then photogrammetry, computer applications, geodesy, then GPS and all. So the major component here in GIS is remote sensing. We are getting the data through satellites, through aircrafts and all. So here remote sensing data processing deals with the real life applications with great societal values. That means, see, we can do urban monitoring, fire detection or flood prediction from remotely sensed multispectral or radar images, which are having a great impact on economical and environmental issues. So remote sensing plays a significant role to treat efficiently the acquired data and provide accurate products. Remote sensing has evolved into a multidisciplinary field where machine learning and signal processing algorithms play an important role nowadays. So here you can see I'm telling a picture is worth 1,000 of words. That too you can see your college only, PA College of Engineering, madam. You can see how best we can make use of this remotely sensed data to get the required information. So this is the latest satellite imagery of PA College of Engineering. So that means it is 2019 data. In a similar way, see what was the condition, how many buildings were there about 5 years back, 10 years back. That kind of things can be monitored with the help of multi-dated satellite data. Of course, you can see this is of 2004 when the college was established. So now coming to geoinformatics. So here in geoinformatics, it is mainly comprises of remote sensing, then surveying. So then we have the database management system, we have the GPS, then computer applications. So finally, we are integrating all these data. So we are getting the required information for a particular geographical area. That is what it is called as geographical information system. And I said in the beginning, remote sensing plays a significant role in natural resources mapping and all, and it is one of the major component of GIS. So here we have to acquire the data. Of course, we are getting enormous data now through satellites. So there is a need to process this satellite data for various applications. When I talk about remote sensing, it has wider applications in the field of earth resources mapping, like natural resources, then natural disasters monitoring, urban sprawl, then coastal zone management related studies, forest related studies, agriculture related studies and all. So here the two basic concepts of remote sensing are, one is data acquisition. We must acquire the data with the help of satellites, or else we have to collect it through conventional technique. But conventional techniques are laborious, time consuming, whereas satellites are providing you the synoptic view, the repetitive coverage, the multispectral information, multi-dated images and all. So we are getting enormous data. So first of all, we have to collect the data. That process is called as or mechanism is called as data acquisition. And once we have the data, that has to be processed. That means we have to do the interpretation, then we are doing the data analysis. So here in remote sensing, we have the sources of energy. So sun is the chief source for the electromagnetic radiation. And before it reaches the Earth's surface, it has to propagate through the atmosphere. So what will happen when the energy passes through the atmosphere? There is a mechanism called scattering and absorption. See, scattering, I will tell you in the subsequent slides what is the significance of this scattering, because that will be considered as a noise in the satellite imagery. Before going for any kind of satellite data interpretation, we must remove that noise. That means due to scattering, the contrast of the image get reduces. That is why I am going to discuss that part also. So propagation, when the energy propagates through the atmosphere, there is a mechanism called scattering and absorption. Depending upon the interacting electromagnetic radiation and the atmospheric particle size, we have Rayleigh scattering, Mie scattering, and non-selective scattering. In the case of Rayleigh scattering, the interacting electromagnetic radiation will have a larger dimension than the atmospheric particles. So blue sky is the result of Rayleigh scattering. In the case of Mie scattering, both the interacting electromagnetic radiation and the atmospheric particles are having the equal dimension. In the case of non-selective scattering, which is the reversal of Rayleigh scattering, that means atmospheric particles will have larger dimension than the interacting electromagnetic radiation. Because of this scattering, see, in addition to the reflected energy of the Earth's surface, the backscattered energy from the atmosphere or from the Earth's surface itself will also be recorded by a sensor of a satellite. Due to this, there will be a noise that has to be removed. So in addition to this scattering, atmosphere does not allow all the electromagnetic radiation to pass through it. Only certain wavelength of the electromagnetic radiation can pass through the atmosphere. So the atmosphere, which is acting as a transparent media, or where the absorption is minimum, that is considered as the atmospheric windows. So we say window shopping from space. So in remote sensing, normally we are sensing from a distance without any physical contact with the object. And here we are making use of the aircraft from lower altitude. You can see here we have the low altitude aircraft, medium altitude aircraft, and we have the spacecraft from higher altitude, maybe from 600 to 800, 900 kilometers. Then we have another type of satellites called Indian national satellites, which are collecting the data from an altitude of 36,000 kilometers. They are geosynchronous satellites. But see, now what happens, we are collecting the data through aircrafts or spacecraft. So we are saying these are the platforms. We have the ground platform, we have the aerial platform, then we have the space platform for remotely collecting the data without any physical contact. So radiation is reaching the Earth's surface, it interacts with the Earth's surface features, part of the light will be retransmitted back, and this retransmitted energy will be recorded by the aircraft or spacecraft. So what happens when the energy interacts with the Earth's surface features? In the subsequent slides, we'll be going to discuss in detail. So now we have the aircrafts and spacecrafts. Aircrafts collect the data in the form of photography, aerial photography. All photographs are images, but all the images are not photographs. In fact, we are recording it in the form of a film in case of aerial photography. In fact, remote sensing began with aerial photography, especially during World War time. During First World War, they started using the aerial photography, and it reached its peak during Second World War. And even in the initial stages, they were using pigeons to take the photographs. And of course, then from 1972 onwards, America launched a satellite called Landsat. From there onwards, operational remote sensing satellite. We are getting the data through spacecraft. So up to this stage, it is called as data acquisition. Now we have the data. So that data has to be interpreted, that has to be analyzed. So we say visual analytics and digital image processing. So through visual analysis, we are making use of the hard copies, the paper prints. Then we are making use of some recognition elements criteria, like the tone, the color differences, the shape, pattern, then associated features criteria. Then we are saying what type of features it is based on the integrated approach. in case of digital image processing, we make use of the computers for processing the data. So digital image processing involves the manipulation and interpretation of digital images with the help of a computer. Of course, this is in case of digital image processing, we can improve the contrast of the image, we can enhance the image because we are interested to get maximum information from the images. So these data are analyzed through visual as well as through computer analysis. Finally, we are generating the data or information in the form of maps, charts and all. Finally, it will be supplied to the users. So from the remotely sensed data, at the end, I will be able to generate a very useful geological map, geomorphological map, soil map, land use, land cover map like that. So that kind of maps can be generated. Of course, we are using different kinds of platforms for remotely collecting the data. We have the ground-based. Yes, see, as you go higher and higher, you will be able to see a larger area. See, that is what you are getting in the case of satellites or aircraft. You are getting the synoptic view or a bird's eye view that we are getting through aircraft, spacecraft, as well as from the ground-based platforms. Of course, we have ground-based platforms. We have airplane-based, that is aircrafts are normally used. They are taking the photographs. In the case of satellites, they are taking the images. See, there is a difference in the case of aerial photography, which makes use of the visible region of the electromagnetic spectrum. That means from 400 to 700 nanometer or from 0.4 to 0.7 micrometer range of the electromagnetic spectrum is used. Whereas in case of remote sensing, satellite remote sensing, beyond the visible region of the spectrum is also used. That means satellites are capable of collecting the data in the visible as well as in the infrared region as well as in the microwave portion of the electromagnetic spectrum. Yes, when we say this GPSC, we have the global positioning system. So through this GPS, we are collecting the coordinates that are the latitudes, longitudes, and elevation of an area. So GPS means it is a constellation of Earth orbiting satellites for the purpose of defining geographic positions on and above the surface of the Earth. There are three segments when we talk about GPS. They are space segment, control segment, then we have the user segment. So in the case of space segment, we have the satellites. So in the initial stages, American satellites, we were using American satellites called NowStar series of satellites. They launched more than 30 satellites for these purposes, but minimum of 24 satellites are required, and they are orbiting at different, see, 55 degree with 55-degree inclination. Each plane has 4 to 5 satellites and broadcasting position and time information on 2 frequencies. So earlier we were getting the data from NowStar, but now Indian Regional Navigational Satellite System, of course, ISRO has launched a series of satellites. About 8 satellites have been launched for this purpose, and that is also popularly called as NAVIC. Through this, we are getting the positions, the coordinates, the latitude, longitude, and the elevation of a particular area. Just now I said we have the space segment, we have the control segment. So to control the satellites, then we have the user segments. That means through GPS device, we are collecting the data. So then IRNSS will provide an absolute position. In fact, this is our own Indian Space Search Organization. They have launched a series of satellites for this purpose to get the coordinates, especially for navigational purposes. Indian Regional Navigational Satellite System will provide an absolute positional accuracy of better than 10 meters throughout India and within a region. The IRNSS system mainly consists of ground segment, space segment, and user segment. So we have the regional navigational system and we have the independence from United States GPS. So now we do not require their assistance. So GPS is not guaranteed in hostile situations. Sometimes if there are some calamities and all, that time it may not provide that kind of information. But the program was approved in May 2006 and now we have reached that we have about 8 satellites for that purpose. Now, when we talk about the components of a GIS, a working GIS integrates 5 key components. They are the hardwares. So we need the computers for processing the data. So computers, then we have the networks. Then we have the peripheral devices. We need the printers, plotters, digitizers and all to digitize the data. Hard copies must be converted into digital data. But now we are getting the digital data itself through satellites, through aircraft and all. Then you require the software. GIS software provides the functions and tools that users need to store, analyze, and display geographical information. The key software components are, we have different kinds of GIS software packages, then we have database softwares, then operating system softwares, then network softwares and all. Then we need the data, especially the data we are getting through conventional technique or through satellite data or through surveying techniques. But the major data, that is the input, comes through remote sensing. When I say remote sensing, we are getting the data through aircrafts or spacecrafts. And the following are different data types. They are available in the vector format, then raster data. So normally satellite images are available in the raster mode, having regular rows and columns. Then we are getting the image data, then attribute data, the spatial data or non-spatial data. Then we need people to do the interpretation. So administrators, managers, GIS technicians, application experts, then end users, then consumers. Then the methods, yes, the guidelines, specifications, standards, procedure and all that we are making use of. So these are the major components of a GIS, geographical information system. And I said just now, the data are available in the raster and vector mode. Raster data, satellite imagery, or whenever you take a field photo, that are all raster data having regular rows and column arrangements. So raster data are described by a cell grid, one value per cell. Whereas, see the point, which is a vector data, line, point, line, and polygons are vector data. Whereas that raster data, see, you have a pixel, regular arrangement of satellite data. So then you have the square blocks or rectangular blocks. So they're all raster data. So satellite data are raster data, and from which you can extract the vector data in the form of map and all. See why GIS is so important. So geographical information system, see, well considered combination of mutually referring data sets of various kinds of position bound thematic data. See, that means we are generating different kinds of thematic maps. We are georeferencing the satellite data. Then we are transferring these details to that of the base map. That means for that purpose, we are making use of the Survey of India topographical maps and all. So all the data are georeferenced. That means whenever you need, for example, if you want to do some groundwater prospecting zone map, so you need different kinds of thematic maps. When I say thematic maps, you see, geology is representing the rock types and structures. So it is called as a theme, geological map. It is a theme. In a similar way, I'm generating the landforms. It is called as geomorphological map. If there is a topographical details, that is topography of the area. So we can represent it in the form of a topographical map. Of course, Survey of India generates the topographical maps. Then we have the soil maps, geological maps, precipitation map, land cover, vegetation. Then by using, see, different kinds of techniques, secondary data, surface temperature, hydrology, population. See, like this, we can extract meaningful information for a particular geographical area, and then we can integrate all the thematic layers and we can derive the required information. Of course, in the beginning, I said photogrammetry or aerial photography is also a part of remote sensing. In fact, aerial photography was the first. In the beginning, remote sensing began with aerial photography. So especially during the World War, they used this kind of technology, and we are deriving some quantitative information based on the analysis of 3D aerial photographs. So that is called as photogrammetry. That means you are deriving some quantitative information and the input is aerial photography. The end product is a topographical map. The quantitative information means on the topographical maps, you have the contours. On 1:50,000 scale, the contour interval is 20 meter, 40, 60. If you want to know the elevation of a particular area, you can make use of these topographical maps. On 2,50,000 scale, the contour interval is 100 meter. On 25,000 scale, the contour interval is 10 meter. That means that quantitative information you have derived by the analysis of photogrammetric techniques. So photos means light, gramma means something drawn or written, metron means to measure. So photogrammetry is the art, science and technology of obtaining reliable information about physical objects and the environment through the process of recording. See, recording means through aircrafts, we are recording the data. Then we are making some measurements. Then finally we are doing the interpretation of the photographic images and patterns. And here the electromagnetic radiation plays a significant role in the sense visible region of the spectrum is used. So where we can make use of these photogrammetric techniques. See, topographic mapping earlier and still now, that means in India, we have a survey of India. The headquarters is located at Dehradun. They generate the topographical maps using 3D aerial photographs, using photogrammetric techniques. And they vary in scale from large to small. Small means when I say, suppose we are considering three scales, one is to 2,50,000, one is to 50,000, and one is to 25,000. Of the three, one is to 2,50,000 is the smallest, and one is to 50,000 is the medium scale, and one is to 25,000 is the largest scale. That means one unit on the map represents that many units on the ground. So with the scale, we will be able to measure the distance between any points. So quantitative measurements are possible. Then used in private engineering and surveying firms. See, topographical maps are very much required whenever we have to go for the generation of the base maps on which we are transferring the other details. Then it will become a thematic map. In planning and designing highways, railroads, rapid transit systems, and even in the construction of bridges, pipelines, and there we need this type of topographical maps. Then see, once the aerial photography is available, then it has to be rectified. So with the help of rectification, we can do some kind of analysis, and the rectified photographs are called as orthophotos. In fact, we cannot make use of the aerial photographs directly to generate the maps, because there will be a variation in the scale from point to point, because the scale of the aerial photography means it is focal length divided by flying height, whereas focal length remains constant. Normally in India, we make use of this 152 millimeter focal length lens for taking the photograph. But the terrain is not flat, it is undulatory. The elevation varies from point to point. So that is why you are getting the scale variations from place to place in case of aerial photography. That is why it has to be rectified, and whatever the errors are there, once the errors are removed, then that process is called as orthorectification, and the orthorectified photographs are used to generate the topographical maps. So we have vertical aerial photograph, we have low oblique aerial photographs, and high oblique aerial photographs. In most of the cases, we go for vertical aerial photography. That means here the optic axis is kept vertical or near vertical, so that we will be getting the vertical. Normally in case of aerial photography, especially in India, we go for 23 centimeter by 23 centimeter format size. So that is the format size of the aerial photography. That is the standard one. And focal length, normally we go for 152 millimeter. Aerial cameras focal length will be 152 millimeter. So here the optic axis is kept vertical or near vertical. So we are getting high precision in case of vertical aerial photographs. In the case of low oblique aerial photographs, see, the optic axis is inclined. When the time of taking the photograph, the optic axis is inclined, but you cannot see the horizon in the case of low oblique aerial photography. Whereas in the case of high oblique aerial photography, the tilt of the camera is sufficient so that you will be getting the horizon. So that is how, see, again you can see here vertical camera axis is kept vertical or near vertical. In the case of low oblique, you cannot see the horizon. In the case of high oblique, you can see the horizon. And these are the resulting photographs through vertical, low oblique and high oblique aerial photographs. Normally we go for vertical aerial photography, and that will be used to generate the topographical maps. Of course, see, through aerial photography also we are getting a lot of data. So that means See, the same piece of land is being photographed from two different angles. Here, see, whenever this, you can see this much area is photographed in the first photograph. The same piece of land is photographed in the second photo also. That means some common overlap will be there in both the photographs. Whatever the features you are observing on the left side of the photo, that is also repeated, being repeated on the right side photo also. That means you have some common overlap. These overlapped aerial photographs or any kind of overlapped images, they are called as stereo pairs. But here we have maximum of 60 to 70% forward overlap along the flight direction between the photos. If first photo number 1 and 2, there will be some common coverage. So that means 50% is required, minimum 50% overlap is required, but safer side we are going for 60 to 70%. So overlap in flight direction, that is 60%. Sideways overlap, that is 20 to 30%. That means that is between the strips. See, this is the flight direction. When it goes in this position, between the photographs, here also you are getting the photographs. Between the strips, there should be some common coverage that is required to compile the mosaic. So projective imaging. So normally aerial photographs are central perspective projection. That means the rays will converge at a point. So that is why they are called as central perspective projection. Whereas the topographical maps are orthographic projections. That means if you join the object and corresponding image points, they move vertically. So here you can see the forward overlap. When the aircraft is here, it takes the photograph of this much area. It covers this much area. Let us say AB. And when it goes to this position, it will cover CD. But see, in this process, CB is common in both the photographs and lap 60% in forward direction of flight. In this process, this much area is common in both the photographs. That is what they are called as stereo pairs. And when I observe such overlapped aerial photographs under the mirror stereoscope, I'm getting the three-dimensional view of the terrain. That means I can measure the height of a particular surface feature, height of a building, height of a particular terrain, Western Ghats, whichever the peak, the highest peak is there. So that height I can measure with the help of aerial photographs. That is what the quantitative information. So I said the end product in the case of aerial photography is the topographical maps. There you are getting some quantitative information. This is between the strips. That is 20 to 30% that is required to compile the mosaic. So of course, this is the end product in the case of aerial photography. You can see the Netravati River and Gurupur River. This is the Netravati Gurupur estuary. And you can see Konaje is somewhere here, your PA college comes somewhere here. So that means there you have the contour lines as well as the drainage networks. So I can generate number of thematic maps based on the topographical map itself. Of course, this is also a output generated based on remotely sensed data product by using aerial photography. Of course, now India has launched few satellites for this purpose. They are called as Cartosat type of satellites. They are again used to generate the topographical maps. So now let us see, in the beginning I said we are collecting the data through aircrafts or spacecrafts. So when the energy which propagates through the atmosphere, there is a mechanism called scattering, then absorption. Finally, part of the light will be reaching the Earth's surface. So that means if we consider the electromagnetic spectrum, we have gamma rays, X-rays, UV rays, visible, infrared, thermal, and microwave portion of the spectrum. So the data is being recorded in different wavelength of the electromagnetic spectrum, but gamma rays, X-rays, and UV rays will be blocked by the atmosphere because atmosphere does not allow all the electromagnetic radiation to pass through it. Only certain wavelength of the radiation can pass through the atmosphere, and those regions are called as atmospheric windows. So we have the visible region, the infrared region. When I say infrared, it comprises of near infrared, mid infrared, thermal infrared region of the electromagnetic spectrum. Then we have the microwave portion of the spectrum that will be reaching the Earth's surface. Now, what will happen when the energy interactions with the Earth's surface features? See, part of the light will be reflected, part is absorbed, and part is transmitted through the object. And this can be expressed by a mathematical equation. EI lambda means ER lambda plus EA lambda plus ET lambda. That means reflection, absorption, and transmittance will be varying. So depending upon the material type and condition. So that permit us to differentiate the Earth surface features on a remotely sensed data. When I say remotely sensed data, it could be an aerial photograph or satellite imagery. So for example, you may have the desert area or the sandy area, which reflects maximum light. Water bodies, which absorbs all the electromagnetic radiation, they look black. So based on that, we will be able to differentiate the Earth surface features. Again, when I am considering this equation, I must remember, again, these three will be different at a different wavelength of the electromagnetic spectrum, in the sense normally satellites collect the data in different wavelength of the electromagnetic spectrum. So in the beginning, I said we have satellites, space shuttles, spaceborne. We have the aircrafts and remote controlled airplanes. They are airborne. Then we have balloons, kites. They are again airborne. Then ladder trucks. They are ground based. So we have ground platforms, we have aerial platforms, and we have space platforms for remotely collecting the data. So just now I said about the electromagnetic spectrum. We have the gamma rays, X-rays, UV rays, then comes the visible region of the spectrum. Then we have infrared, radar, and longer wavelengths, radio waves and all. But see, when these wavelengths, gamma rays, X-rays, and ultraviolet rays, when they passes through the atmosphere, they got blocked by the atmosphere. That means whenever we talk about the terrestrial remote sensing, these wavelengths are not at all playing any role, because this energy will not be reaching the Earth's surface. Whereas visible region of the spectrum, infrared region of the spectrum, microwave region of the spectrum, they reach the Earth's surface, they interact with the Earth's surface features, and retransmitted energy will be recorded by the sensor of an aircraft or spacecraft. So that is what energy reflects, absorbed, and transmitted will vary. So for different Earth surface features, that is the basic principle we are following whenever we are doing the interpretation. See, even within a given future type, the proportion of reflected, absorbed, and transmitted energy vary at different wavelengths. That means, see, if you consider the multispectral scanner of Landsat, there are four spectral bands. When I say four spectral bands, means they're simultaneously recording the signals at a different wavelength of the spectrum. If I'm not in a position to differentiate two surface features at one particular wavelength, I can go for the other wavelength, green region of the spectrum, red region of the spectrum, near infrared region of the spectrum, and there these two features will behave differently. So if we plot the spectral reflectance versus wavelength, normally how much of energy reflects back, and if you divide it by the amount of energy incident upon the object, then multiply it by 100, you are getting the spectral reflectance in percentages. And if you plot the spectral reflectance versus wavelength, see, this is the equations: energy of wavelength lambda reflected from the object divided by the energy of wavelength lambda incident upon the object multiplied by 100. So spectral reflectance is always expressed in percentages. So of course, this is the ground platform we are normally using to take the photographs. Just now I said a picture is worth 1,000 words, and from a higher altitude you will be able to see a larger area. And see, if you plot the spectral reflectance, just now I said spectral reflectance are normally expressed in percentages. And if you plot the spectral reflectance versus wavelength, you are getting the spectral reflectance curves. See, for example, this is the spectral reflectance curve for vegetation, wherein you are seeing a peak here in the green region of the electromagnetic spectrum. Normally, vegetation absorbs blue and red region of the electromagnetic spectrum, and which reflects in the green region. That is why there is a peak, and in the blue and red you have the dips. But you see here, immediately after the red, you have the near infrared region of the electromagnetic spectrum. I said in the beginning, satellites are capable of sensing not only in the visible region of the spectrum, they can sense beyond the visible region of the spectrum. That means, like our eyes, there are eyes present in the satellites called sensors, which are capable of sensing the surface features at a different wavelength of the electromagnetic spectrum. So if you see here, vegetation reflects about 40 to 45 or 50% of the light in the near infrared region of the spectrum. Then we have two dips at 1.4 and 1.9. that are mainly because of the water molecules present in the leaves. They absorb the electromagnetic radiation. See, now by plotting the spectral reflectance curve, I will get some idea about the spectral characteristics of the Earth surface features, and based on that I can select which are the best bands for a particular application. See here, definitely I will prefer the near infrared band, because in the near infrared region of the electromagnetic spectrum, vegetation reflects maximum light. That the reflectance is mainly because of the internal structure of the plant leaves, the presence of chlorophyll and all. And if you see here, the soil, again, it shows the increasing trend, but again, there are two dips almost coinciding with the vegetation. That means water molecules present in the soil, they absorb the radiation. Then if you go for water body, see from 0.7 onwards, there is no reflection at all. That means water bodies absorbs all the electromagnetic radiation. They look black. That means normally in digital data, we are representing this with the radiometric resolution, the sensitivity of the detector. See, if it is zero means through visual technique, I am saying it is showing dark or very, very dark. But when I am doing the interpretation through computers, I will be assigning a value of zero because it is expressed in bits 2 to the power 8. Normally, most of the satellites records the data in 8 bits. So 2 to the power 8 means 0 to 255 quantization levels are there. 0 means darkest object, 255 is the brightest object. So like that, see here it is showing almost to zero reflectance in the near infrared. So to delineate the water bodies, I will prefer the near infrared band. And I said again, see, we have the multispectral data. This is of course an example of Landsat MSS, the American satellite. The first American satellite was Landsat, which had multispectral scanner and return beam Vedicon sensors. This is of course the multispectral scanner data. See, blue region of the spectrum, you have green region, red region, near infrared region. So that means whenever a particular satellite passes over an area, it records the signal simultaneously in the blue region, green region, red, as well as in the near infrared region of the electromagnetic spectrum. That means I am getting multispectral data. Now, let us see why we need this multispectral. See, when I go for the interpretation of this satellite data, so my aim is to differentiate two types of vegetation. Let us say coniferous trees with the narrow-leaved species, whereas deciduous trees, they have broad leaves. So I have to differentiate these two types of vegetation, coniferous and deciduous, narrow leaves and broad leaves. So how to differentiate? I will go for multispectral data analysis. First, I will make use of the blue region of the spectrum. In that wavelength, 0.4 to 0.5, both of these features, coniferous as well as deciduous, are having almost similar reflectance or absorption. They are having absorption here, but here in the green region, they show a little bit higher reflectance, but that is not sufficient to differentiate where we have the deciduous trees, where we have the coniferous trees. If the task is given to you to identify the forest cover along the western Ghats of Karnataka or along the western Ghats of Kerala, there is a need to differentiate what type of forests are there, where you have the deciduous, where you have the coniferous. So to differentiate that, I am going for multispectral data analysis, and I will not succeed in blue green. Then even in the red also, both of them are all having almost similar absorption. But you see in the near infrared, that is from 0.7 onwards, see, coniferous trees are showing a reflectance less than 30%, whereas the deciduous trees are showing a higher reflectance, more than 40%. Now the difference is sufficient so that I can easily demarcate these two vegetational classes. So that is possible with multispectral data analysis. So there is one more formula called normalized differential vegetation index. There I am using the near infrared band as well as visible red to differentiate where I have the healthy vegetation, where I have the diseased vegetation. See, if you get higher NDVI value, that is called as normalized differential vegetation index. So you have to take the ratio of the near infrared as well as visible red. The formula is NIR minus visible red divided by NIR plus visible red. So if you get higher value, so here For the healthy vegetation, see, it reflects about 50% of the light in the near infrared, and of the visible, it reflects just 88%. Now you take the ratio of the near infrared and visible red, 0.50 plus 0.08 divided by 0.50 plus 0.08, you are getting a value of 0.72. That means higher the NDVI, this is the healthy vegetation. So if you get higher NDVI values when you are analyzing the satellite imagery, for a particular area where you have the vegetation or forest coverage, so you can say whether it is healthy or diseased vegetation. Healthy vegetation will always have higher NDVI values, and when the plant is subjected to some sort of stress, see, the chlorophyll production gets reduces. The result is it turns to yellowish. That means there is a combination of green plus red. So part of the light will be reflected in the green, part is reflected in the red. Combination of that will result as yellow patches. And if you get lower NDVI, see here it is 0.14. That means it is a diseased vegetation. So like that, whenever you have the satellite images, yes, you can make use of that. So satellites are providing you enormous information. So from the data, you can extract the required information. So several gigabytes, terabytes of or picobytes of data every day the satellite transmits the signals. So here, if we consider, there are thousands of satellites orbiting over the globe. So now there is no space where to launch the satellite and all. That is why an international commission has been set up, and they are allotting the slots where to launch the satellites and all. So we have geostationary satellites. They are having an altitude of 36,000 kilometers, stationary with respect to Earth. They are orbiting the Earth at a distance of 36,000 kilometers. Of course, India too launched, Indian Space Research Organization launched a series of satellites under INSAT series, and recently we launched one communication satellite last week. So they're all geostationary satellites having an altitude of 36,000 kilometers. They are providing the required information related to weather. See, that is being used for meteorological applications, weather prediction, and even to get more TV programs. So it is a joint venture of All India Radio, then Indian Meteorological Department, Doordarshan, and all India Radio. So number of organizations have been involved in that. So that is mainly useful for communicational purposes. See, as well as to get the required information related to the existing weather conditions, the cloud top temperature, the liquid water vapor content of the atmosphere, and long wave, outgoing long wave radiation, the cloud movement and all. Those kind of things can be studied through Indian national satellites or geostationary satellites. There are hundreds of satellites orbiting over the globe. In a similar way, for natural resources mapping, we have sun synchronous satellites. Their altitude is around 700 to 900 kilometers, and they are providing the required information about the Earth surface features, sun synchronous. They are very useful for natural resources mapping. So some of the current satellites are capable of providing even 30 centimeter resolution. So they are polar orbiting sun synchronous satellites. Of course, we have Indian remote sensing satellites. They are sun synchronous satellites. They are very useful for natural resources mapping. So this is, of course, the Landsat MSS. Landsat was the first satellite launched by NASA of USA in the year 1972. That satellite carried return beam Vidicon, collected the data in 3 spectral bands, and multispectral scanner collected the data in 4 different wavelengths of the electromagnetic spectrum. So this is, of course, the latest Landsat satellite, see, which is having a sensor called thematic mapper. Whereas Landsat was collecting the data with 80 meter spatial resolution, whereas thematic mapper is having a spatial resolution of 30 meter. So I will be discussing these things in the subsequent slides. We have different kinds of resolution whenever we talk about a satellite. So this satellite is capable of detecting even 30 meter by 30 meter object of the Earth's surface, and which provides a little bit higher resolution images. Then see the latest satellite, Landsat 8 products, see, which provides 11 bands of data. So you are getting 11 bands. That is what it is called as multispectral. Whenever this satellite passes over Mangalore area today, we are getting the data in 11 different wavelengths of the electromagnetic spectrum, and each band has its own significance. See, for example, band 1, it is useful for coastal aerosol related studies, and you can see here the bandwidth 0.43 to 0.45 micrometer. That means it corresponds to the spectral resolution. So again, you have the band 2 blue region of the spectrum, and the wavelength is also provided green, red, near infrared. Then we have 2 shortwave infrared, 1 panchromatic band. Then we have to study the cirrus clouds, especially to know what type of clouds are there. Then there are 2 thermal bands. Totally, there are 11 spectral bands. So here you are getting the emitted radiation, whereas in the remaining, see, thermal infrared means it is not the reflected energy. The sensors are recording the emitted energy. The absorbed energy will be emitted back, and that will be recorded by a thermal sensor of a satellite, whereas the remaining sensors with remaining bands, through that we can measure the reflected energy. Of course, this is the satellite launched by France. So this satellite provided 3D images of the Earth's surface. This was the first satellite provided 3D images of the Earth's surface. See, if this is nadir weaving, straight away it is vertically seeing downwards. But when the satellite goes to another position after few days, again the camera can be tilted in such a way that the area imaged about 5 days back or 6 days back will be imaged once again. Like that, the same area will be covered from different angles. In this process, you are getting the 3D view of the terrain, and this was the first satellite provided 3D images of the Earth's surface. Then, depending upon the orbits of the satellites, see, we have geostationary satellites having an altitude of 36,000 kilometers. Just now I said we have polar orbiting. The height varies from 700 to 20,000 kilometers. Most of the remote sensing satellites are having an altitude of 700 to 900 kilometers. And we have the GPS satellites. In the beginning, I said Navstar series of satellites. Then we have our own Indian regional navigational satellite system, popularly called as NAVIC. They are having an altitude of 20,000 kilometers. They are useful for navigational purposes to get the positions of a particular area. Then we have lower Earth orbiting satellites, which are having an altitude of less than 700 kilometers. So the 2 basic satellite orbits. See, we have the polar orbiting satellites, we have the geostationary satellites. See, normally polar orbiting satellites orbit is near polar. They are orbiting from north to south. Now, what happens by the time the satellite completes one full cycle? See, let us say it takes about 90 minutes to make one revolution, covers different areas, each orbit as Earth rotates, and which provides a detailed images. Then we are getting the time sequence. That means time series data we are getting through polar orbiting satellites. Whereas in the case of geostationary satellites, they remains over same portion of planet by revolving with same period as Earth's rotation. So they are having an altitude of 36,000 kilometers, can provide full disk or smaller views. They are not at all provides the highest spatial resolution, maybe kilometer or some meter resolution, not 30 centimeter or 20 centimeter resolution you are getting through geostationary satellites. They are providing coarse resolution, and they are useful for weather and communicational purposes. Just now I said we are getting 100, 500, 1,000 channels, TV programs, or we are communicating through our mobile network. All these are possible through Indian national satellites. So they are all geostationary satellites. Of course, this is the spot satellite, and these are the polar orbiting satellites. See, their orbit is near polar, and this solid line is the satellite orbit, and on the ground they are represented by dashed lines. That means that much area's radiation will be recorded by a sensor of a satellite. Whenever the satellite passes over an area, it collects the data of the ground. See, let us say if it is 185 kilometer on the ground, see, it covers 185 kilometers. That much area's radiation will be recorded by a sensor during its passage from north to south. So they're always passing the equator at the same local sun time. That means if a particular satellite passes over Mangalore coast today around 9:30, whenever it comes over Mangalore area after 18 days or 22 days, the time will be exactly same. If it is 9:30 today, after 22 days, whenever it passes over Mangalore, the time will be exactly 9:30, so that we can monitor the dynamic changes with ideal conditions. And these are the geostationary satellites having an altitude of 36,000 kilometer. And here you can see this solid line is the satellite orbit. This is in the case of Landsat. Let us see, the altitude of the satellite is around 705 kilometers, and the dashed line is on the Earth, how much area's radiation will be recorded. That is called as the swath width. So here the inclination of the satellite is in such a way that they always passes the equator. See, time of day 9:45 a.m. local time. They always passes the equator at the same local sun time, because the inclination is in such a way, it is 98.2 degree. So it always passes the equator at the same local sun time. So if the orbit period is 98.9 minutes. Now let us see how the satellites collect the signals. The satellite orbit is from north to south, whereas the Earth is rotating from west to east. Now, what happens by the time the satellite completes one full cycle of the Earth? The Earth is also rotated from west to east. That means there will be large gap between successive orbits on a given day. However, with each new day, the satellite progresses westwards, and which will overlap the orbit patterns of the previous day. That means if this is the first orbit of the satellite today, around 9:30 or 10:30, the second orbit will be at a gap of 2,752 kilometers at the equator. There will be a large gap between successive orbits on a given day. You will have 14 orbits, let us say, but there will be a large gap between successive orbits on a given day. But what happens if this is the first orbit over Mangalore area today? The second orbit will be somewhere here. Third orbit will be at a gap of 2,700 and odd kilometer. But what happens? The second day's first orbit will be adjoining to the first orbit of the previous day. Second orbit will be adjoining to the second orbit of the previous day. Like that, on the second day, again, you have 14 orbits. Third day, you have 14 orbits. In a span of 18 days or 22 days, again, it depends upon the swath width of the satellite, this width. If the width is more, it requires less number of days to complete the full coverage of the Earth. But in the case of Landsat, it is about 185 kilometers, the swath width. That much area's radiation will be recorded by a sensor of a satellite. So large gap will be there, but the second day's first orbit will be adjoining to this orbit. Like that, second day you have 14 orbits. That means in a span of 18 days or 16 days or 22 days, the entire world will be covered, and the satellite will be in its original position after 20 days. If it is over Mangalore area today, again after 22 days, it will be over Mangalore area. That means if you divide 365 by 20 days or 18, that number, about 20 times the same satellite will pass over an area. And this concept is called as multi-dated imaging. And we are getting multispectral as well as multi-dated data through remote sensing. So these are the data. And when we analyze this data, we are getting some useful information about the natural resources or urban related studies. If we are carrying out, we can extract the meaningful information based on the analysis of remotely sensed data. Now we have, see, camera aerial photography. The entire area will be photographed at a time, and there the visible region of the spectrum is used. And in the case of digital recording, see, we have whisk broom scanners or across track scanners. We have push broom scanners, or we have along track scanners. See, especially in the case of Landsat satellites, they are collecting the data across the flight line. That means they are considered as whisk broom. If the flight direction, if the satellite movement is from north to south, it scans from west to east. So these are the scan lines, and in each scan line you have number of pixels, picture elements. So that is across. That is why they are called as whisk broom scanners or across track scanners. In the case of push broom scanners, there are linear array of detectors comprises of charge coupled devices, which are electronic silicon chips, which are more sensitive to light than ordinary films. So there is no moving part. The entire area's information will be recorded. So that is called as push broom or along track scanners. So then when we talk about remote sensing, see, we have multi-concept. Multi-concept means that is being employed in remote sensing. So different platforms, different altitudes, that is multi-stage. See, yes, we have the low altitude aircrafts, medium altitude aircrafts. We have the spacecraft from 700 to 900 kilometers. We have GPS satellites orbiting at an altitude of 20,000. Then we have the geostationary satellites at an altitude of 36,000 kilometers. So data acquisition approach, multi-concept. See, then different platforms and different altitudes, they are considered as multi-stage. Then different dates per time, that is multi-temporal data. See, we are getting multi-temporal, more than one dated data we are getting through satellites. That is in case of a single satellite, but we have constellation of satellites, group of satellites. That means every day one or the other satellite will be passing over our area and we can collect the required information. So that is why it is called as multi-temporal. That means more than one dated data. With that we can monitor the dynamic changes. What was the condition of a particular city about 40 years back, 30 years back, urban sprawl related studies, coastal related studies. What was the condition of Netravati Gurupura estuary or Mulki Pavanja estuary, Ganguli estuary about 40 years back? What is the present scenario? How much of forest area degraded over a period of time along the western Ghats of Karnataka? Yes, these kind of studies can be carried out so that I can monitor the dynamic changes by using more than one dated satellite data, time series data. So that we are getting through satellites. Then different sensors. Yes, I said we have the multispectral scanners in case of Landsat. Then we have thematic mapper, we have enhanced thematic mapper, we have HRV sensor and all. So we are then, if we talk about Indian remote sensing satellites, we have list 1, list 2, list 3, different types of sensors with different resolutions. So with that we can gather the required information. Then we have different spectral bands, multispectral, simultaneously recording the signals in the blue region, in the green region, in the red region, in the infrared region of the electromagnetic spectrum. That concept is called as multispectral concept. Then coming to the resolution, see, these are very important because we are getting the satellite data. And before going for any kind of analysis through visual or through digital image processing techniques, we talk about this machine learning, supervised classification, unsupervised classification, and all we can carry out with the help of satellite data. But before going for any kind of satellite data interpretation, we must have the knowledge. See, what is its spatial resolution? That means how much area will be covered by a satellite. See, minimum area of the ground which can be resolved by a sensor is called as its spatial resolution. How much area's radiation at a time, that is also called as instantaneous field of view. So the size of the field of view, example 10 meter by 10 meter, yes, that much area's radiation will be recorded, and it is recorded in the form of a pixel on the digital data. So minimum area of the ground which can be resolved by a sensor of a satellite is called as its spatial resolution. Coming to the spectral resolution, at what wavelength of the electromagnetic spectrum the data is being recorded. Here see, the data is being recorded in the blue region, green region, red, in the near infrared at a different wavelength of the electromagnetic spectrum. The number and size of spectral regions, the sensors records data in blue, green, red, or near infrared, or thermal infrared, or microwave. And when we talk about microwave, that is nothing but the radar technology, radio detection and ranging technology. So at a different wavelength of the spectrum, so each band has its own significance. So with that, we can collect the required data at a different wavelength of the electromagnetic spectrum. Then temporal resolution means how often the sensors acquire data. Example, every 30 days or every 20 days or every 16 days. And some of the satellites are covering the area twice a day. There is a sensor called AVHRR present in NOVA series of satellite. This NOVA American satellite covers an area twice a day. You have the morning pass, you have the evening pass, especially for potential fishing zone mapping and all. We require the frequent revisits. So that is possible through very high temporal resolution satellites. So they are providing very high temporal resolution. Every day the satellite will pass over an area twice. So some of the satellites require 20 days, 30 days like that. So, but anyhow, with this temporal resolution, we can monitor the dynamic changes. What was the condition earlier and what is the present scenario. That is possible. And when I say the radiometric resolution, the sensitivity of detectors to small differences in electromagnetic energy. That means in the beginning I said normally the radiometric resolution ranges from 0 to 255. In majority of the satellites it is 8 bits. In the initial stages for Landsat MSS it was 6 bits, 2 to the power 6, 2 into 2 into 2. That means the lowest DN value or brightness value is represented by a value of 0. The brightest signature, the maximum reflectance, is represented by a DN value or brightness value of 63. If it is 6 bits, in our Indian remote sensing satellites, it was 7 bits, 0 to 127 quantization level. 0 is the darkest object. That means it absorbs all the electromagnetic radiation, whereas 127 means it is the maximum reflectance. In case of 0 to 255, 0 is the darkest object, 255 is the brightest. That means maximum reflectance. That is how we can differentiate the earth surface features. See here, the difference between 0 and 1, if the values are 254 and 255, yes, we can differentiate the surface features based on these digital numbers or brightness values. That is the advantage in the case of digital image processing. So here again in detail, we have the spectral resolution. In case of Landsat, it is thematic mapper 30. It got improved in case of Indian remote sensing satellite 23 point, spot satellite 20, then spot satellite 15, then IRS spot 4 panchromatic 10 meter, IRS 1C 1D 5.8 meter. And some of the current satellites are providing less than a meter resolution images. That means a vehicle moving on the road can be detected through satellites, and I can easily differentiate whether it is a bike or scooter. That is possible with the finest resolution images. Then we have the Landsat. See here, the coarse resolution, here the finer resolution. Finer the resolution means we can easily differentiate the earth surface features. And this is spectral resolution. At what wavelength of the electromagnetic spectrum the data is being recorded, and in how many spectral bands. When I say MSS of Landsat, it collected the data in 4 bands, whereas thematic mapper collected the data in 6 bands, and now the latest Landsat TM collects the data in 11 different spectral bands. So like that, in the initial stages, the surveys were carried out once in 50 years and all. They generated the maps using conventional technique and other surveying techniques. But now the satellites, during the satellite era, we are getting every day, once in 30 minutes, we are getting the different kinds of data through geostationary satellites. So that is possible. Every 30 minutes we are getting. That is called as the time series data, temporal resolution. And this is the 8 bits data. 1 bit means you cannot see the features clearly. It is 0 to 255. Now some of the satellites, 9 bits, 512, 10 bits, 1024, 11 bits, 2048, 12 bits, 4000 and odd. So that kind of informations are available. And if you see here 2 satellite data, this is coarse resolution, one of the Olympic venue you can see with the rectangular block, but you cannot see because this is the coarse resolution 20 meters spot satellite data with 117 kilometers swath width. But if you analyze the same area with the ICONOS with 13 kilometers swath width and 4 meter resolution, see the playgrounds are clearly visible here, and even the settlements and adjoining areas, circular shaped playgrounds, diagonal shaped or rectangular shaped. See, all these features you can easily differentiate where you have the rectangular blocks, square blocks, and what is the shape of the playground. So based on that, you will be able to differentiate the surface features clearly. That is why it is providing very high resolution. See, you can see here from the coarsest to the finest. Here you cannot see any settlements and all, but when you go for 0.5 to 0.5 meter resolution images, the individual houses can be differentiated. So that is the advantage of high resolution images. Yes, you can see a resolution comparison, 1 kilometer resolution. This is a color composite. See, wherever red color is there, that are all vegetated areas, because in the beginning I said vegetation reflects maximum light in the near infrared region of the electromagnetic spectrum. That means wherever vegetation is there, that are all represented by red color. Of course, this is 1 meter spatial resolution ICONOS. panchromatic black and white imagery. Here again, you can see the panchromatic multispectral data and all. So temporal resolution means just now I explained the capability of a satellite, how many times it passes over an area so that you are getting the repetitive coverage. So here again, you can see very clearly provided in this slide, you can see July 10 means again it passes over that area on July 10th, August 3rd, like that. So you are getting the time series data. And the radiometric resolution you see here, 2-bit means it is 0 to 4, 2 to the power 2. 6 bits means 0 to 63. 0 means I said these are nothing but the brightness values. 0 is the darkest, 63 is the brightest. Here 8 bits means it is 0 to 255. 10 bits means it is 0 to 1023. And see here you can see the individual bands, blue region of the spectrum, green region, red region, and near infrared region. But here, see, when I use this blue or green region of the spectrum or red region, I cannot differentiate the surface features clearly. But when I go for near infrared band, see, water bodies are very clear. And I can easily demarcate the boundary between the two, land surface features and water body. So this is the multispectral image, and you have the 4 bands of multispectral data. So they are used to detect different surface features. And see here how rivers are better detected with bands at top right. You can see here how best you can make use of this multispectral data to differentiate the surface features. Of course, see, we are all application oriented, but to see, whenever I am basically a geologist, when I am going for the interpretation of the satellite data, my aim is to extract maximum information from the images. But if I make use of the computer programs, and if I am in a position to extract maximum information by different techniques, by supervised, unsupervised classification, or by another technique, principal component analysis, see that information I can make use of whenever I am generating a useful resource map. It may be a geological map or geomorphological map. There, yes, we must have the knowledge of these machine learning languages or some other languages, how to do the supervised classification, how to do the unsupervised classification, what are the main differences between these. See, the bands can be combined to produce a composite image bottom and colorized in order to show much more than what could be seen with the naked eye alone. See, when you combine these 3 bands, you are getting the true color. That means vegetation will be shown in the green color. But here it is represented with the red color. The fact is the combination of green, red plus near infrared using appropriate filters, they have generated the false color composite. Of course, this is a false color composite because vegetation is represented by red color, and vegetation reflects maximum light in the near infrared region of the spectrum. That is why normally vegetation is represented by red color, and the difference in red, that will tell me what type of vegetation is existing, where I have the dense vegetation, where I have the diseased vegetation, where less vegetation, or the barren land. See, these are the spectral reflectance curves. In the beginning, we have discussed about these things. When I combine blue, green, red, I will be getting the true color imagery. And when I am combining green, red, and near infrared, I am getting the false color composite. And with this, I can differentiate more number of surface features. So these are all satellite data, and they're providing enormous information. See, of course, this is the Indian imaging systems. In fact, India launched the first satellite in the year 1988 called Indian Remote Sensing Satellite IRS-1A. The subsequent satellite was launched in the year 1991 called IRS-1B. And we have launched more than 50 to 60 satellites under IRS series and around 50 to 60 under Indian national satellites. So more than 120 or 130 satellites have been launched so far by using our own launching vehicles and all. So we have the Cartosat, which provides now the latest Cartosat provides 30 centimeter resolution images, and that is being used for cartographic applications, especially for map making. Then 1C, 1D. See, after 1A, 1B, we launched 1C, 1D during 95 and 1997 respectively with higher resolution. Then we launched OceanSat, IRSP4, OceanSat, IRSP6, ResourceSat. So like that, we are launching every year, we are launching number of satellites for specific applications. And with that, we can extract maximum information. See, this is how the Indian Space Research Organization. So we have the satellite launch vehicle. We have developed that also. Launching vehicle technology from augmented satellite launching vehicle to PSLV, polar satellite launching vehicle to geostationary satellite launching vehicle. So we have different types of launching vehicles, and at the same time, we are using this data for number of applications. See, we have coarsest resolution to the finest resolution satellite images are available that we can make use of for number of applications. See, launch vehicles and all, even we have developed this cryogenic technology, and through that we can launch the satellite to the height of 36,000 kilometers. So satellite evolution, when we talk about the satellite evolution, see, remote sensing satellites, we have high resolution imaging, then multiple payloads. Payloads are nothing but the sensors. When I say IRS-1A, 1B, which carried LIS-1 and LIS-2 sensors with 72.5 meter and 36.25 meter spatial resolution. Then we have 1C and 1D with 23.5 meter, 5.8 meter resolution images and all were available. Like that, we have the ResourceSat, CartoSat, and now we are getting even 30 centimeter resolution images. And see here, when we talk about the satellite data, yes, we can make use of this for a number of applications. See, food security and poverty alleviation, then infrastructure, social and physical, natural resources, assets build up, disaster management support, weather and climate related studies. Of course, see, if you see individually, we can go for agroinformatics, agricultural related studies, the vegetation resources, agricultural resources. We can extract the forest resources information is also possible. Then potential fishing zones. See, we can measure the sea surface temperature as well as the ocean color information. And when we integrate these two, based on that, we can generate the potential fishing zone maps. And based on that, we can direct the fishermen where to go for fish catching and all. So that is possible with the ocean related satellites and NOAA series of satellites. Then drinking water mission scheme. Yes, how best we can make use of our remotely sensed data to get the required information related to drinking water. Then wasteland inventory, where we have the wastelands and all. So with the courses to the finest resolution, we can study all these aspects. Then watershed development, yes, watershed, what type of resources are there, how much water is available, how much of soil resources are there, vegetation resources, and how to prioritize the watershed, and what are the measures one has to take for the improvement of the watershed or the development of the watershed. See, all the required parameters I can extract meaningfully by the analysis of satellite data. Then we have the urban information system. Then we have railroad pipeline alignment, food monitoring, drought assessment, cyclone warning, landslide hazard zonation, and biodiversity assessments and all. These are the applications where we can go for satellite images. Of course, this is for the tele-education. In fact, we are using EduSat. Even the remote villages can be connected through the satellites, and we can provide the education for the villages with the help of these satellites. Then telemedicine, even the hospitals, health specialist centers through video conferencing, and panel of doctors will be there, and referral hospitals will be there. So we can communicate with the experts. So that is possible with the telemedicine through satellites. Of course, Chandrayaan-1, we have sent satellite to moon also. So I will be discussing some more aspects of this Chandrayaan program in the subsequent slides. But see, we have sent satellite to moon, and we have sent one more satellite, Chandrayaan-2, that is called as. Now coming to the Earth observation application. See, now we have the satellite data. Photons. We have the satellite data. See, we have the satellite data, and that can be used for a number of applications like agriculture and soil, crop acreage and production estimation, soils and land degradation mapping, watershed development, horticultural mission for Northeast, then forest environment and biodiversity related applications, forest cover, then type mapping, forest fire and risk mapping, then environmental impact studies, then water, potential drinking water zones, command area management, reservoir sedimentation, then for land applications, land use, land cover mapping, wasteland mapping, urban sprawl related studies, large scale mapping. I said small scale to the largest, even the village level maps can be extracted through remotely sensed data. then weather and climate related studies, extended range, monsoon forecasting, ocean state forecasting, then regional climate models and all, then potential fishing zone. When we talk about the ocean related studies, coastal zone mapping, then disaster support, flood damage assessment, drought monitoring, and landslide hazard zonation mapping and all. For these purposes, we can make use of the satellite data, and there are a number of sensors available from the coarses to the finest resolution, that is considering the spatial resolution and number of spectral bands. And there are a number of spectral bands available in the blue, red, then infrared region of the spectrum and all. This is of course the evolution of the Indian remote sensing satellites. Of course, the individual trees can be identified with the help of high resolution satellite data. Of course, you can see Bangalore and its adjoining area. Then what are the advantages when we talk about the satellite? See, they are providing enormous data, remote sensing. See, you are getting enormous data. So synoptic coverage, that means, see, it provides a bird's eye view. Of course, this is the Himalayan terrain. You can see the Manasa Sarovara, the glaciers, then the vegetated covered areas, forest areas, and other landforms. The topography of the area is clearly brought out here. So you are getting the synoptic coverage, the bird's eye view. Then it provides the repetitive coverage. That means same area can be covered number of times, so that you are getting the multi-dated images, time series information, so that you can monitor the dynamic changes. What was the condition? See, this is the advantage in case of satellite data. So inaccessible area coverage, yes, definitely we may not be able to cover each and every part of the Himalayan terrain or the Western Ghats. But if you are really good in interpreting the satellite data without visiting the areas, you can collect the required information. What type of vegetation, what type of forest is there, how much water is available in a particular reservoir. You can calculate the aerial extent of that water body. That is what it is called as the spatial data. Then at the same time, you have to collect some attribute data, non-spatial data. Then if you integrate, you will be getting the required information. See, information in spatial domain, that is what the spatial information, 52 square kilometer, 32 square kilometer. When I say PA College of Engineering, how much area it occupies, how much of campus they have, that is the spatial data. Then how many departments are there, how many faculty are there, male, female, then students, all these are considered as the non-spatial data. Then I am getting the coordinates information. Then finally I will be integrating all these, so spatial and non-spatial data. Then it will become a geographical information system pertaining to that campus, PA College of Engineering. That is how we have to generate the geospatial data. But for that we need, see, maybe for smaller area, yes, conventional techniques are okay. But whenever I am covering larger area, maybe the taluk or the district or the state, I may not cover each and every part of the state or district at regular intervals. The alternative is the satellite data. With that, I am getting the synoptic view, repetitive coverage, so that I can cover each and every part of the state. Information in spatial domain, then data is quantifiable. Yes, I can get the required information, how much area this building occupies. So that is quantifiable. Then large archives of historical data are available. That means what was the position about 30 years back, 20 years back. See, that kind of information I'm getting through satellite data, historical data, 72. I said in the beginning, the first satellite was launched by NASA of USA in the year 1972. And from 1972 to 2020, in a span of 48 years, what are the significant changes occurred in and around our Mangalore University campus or in and around PA College. In fact, if you analyze the satellite data of 1972 pertaining to PA College campus, there was no built up area at all. It was a barren land. But slowly built up areas have come up. Now you have a large campus. So that means you can monitor these kind of changes with the help of multi-dated satellite data. And here, see, when we talk about this broadband, see, visible or shortwave infrared, the wavelength 0.4 to 0.7, it is a broadband, or 0.4 to 0.9, it is a broadband. Then the same, we are splitting it into different regions of the spectrum, multispectral, band 1, band 2, band 3, band 4, band 5, band 7, like that. At a different wavelength of the spectrum, we are getting the data with the 7 bands, 12 bands, like that. But whenever we go for hyper spectral remote sensing, there we are getting the data in hundreds of spectral bands. So then in the near future, we are going for ultraspectral with thousands of spectral bands. See, there is a difference between multispectral and hyperspectral. Multispectral means many spectra, maybe 7 bands, 8 bands, or 12 bands at the most. But they are having broad wavelength. That means 0.4 to 0.5 or 0.5 to 0.6, or if it is in nanometer, 400 to 500 nanometer. Whereas in hyperspectral, the bandwidth is less. If it is zero point 0.4, 400 in nanometer, 400 to 401, 401 to 402, like that. In between 0.4 to 0.5, you will have 100 spectral bands. That means in hyperspectral remote sensing, the number of bands are more. At the same time, they are contiguous bands. There is no break between the bands. If it starts at 0.4 and if it ends at 2500, you will have contiguous spectral bands in the case of hyperspectral, and which provides more information. And see, now whenever you have this kind of big data, metadata, how to process the satellite data, yes, there we need some of these computer programming languages. So maybe you have to develop some more programs. So with that, we can analyze the satellite data with better accuracy and all, whatever the algorithms are available, and that we have to make use of. At the same time, there is a need to fine tune these algorithms so that we can extract maximum information from the remotely sensed data. We have multispectral data available with us. We have hyperspectral data are available with us. Then different wavelength of the spectrum are normally used. See, whenever I'm talking about the satellite data, which are having regular rows and column arrangements, this is nothing but a raster data. In fact, satellites are providing the raster data information, rows and regular columns. Of course, this is the scan line. And in each scan line, you have number of pixels. Of course, this is the picture element. And this digital number and this square block, its size represents the spatial resolution, and this number represents the radiometric resolution. The brightness values or gray level values are the digital numbers. The analog values will be converted into digital numbers. That data will be transmitted to the earth receiving station, and we are getting the required information. And in fact, these are the digital image data formats. So we have the data are available in different spectral region of the electromagnetic spectrum. So pictorial representation, what is an image? Which is a pictorial representation of an object or a scene, consists of tiny equal areas called picture elements or pixels arranged in regular lines and columns. That is what I said. A satellite imagery is a raster data having regular rows and columns, and the process of recording these brightness values is called as scanning. And in each scan line, you will have number of pixels. That pixel represents the spatial resolution as well as the radiometric resolution. The minimum area of the ground which can be resolved by a sensor is called its spatial resolution. And what is the digital number brightness value? It is represented with the radiometric resolution. Each pixel represents an unit area on the ground called ground resolution cell. So it is an array of numbers depicting spatial distribution of a certain parameter such as reflectance, temperature, geophysical data, elevation, like that. So if it is 8 bits of data, normally in the case of satellite, most of the satellite data are available with 8 bits, so 0 to 255. So X and Y define the location of each pixel, and Z giving the DN value, which can be displayed as grayscale or intensity value. So what are the advantages of digital image processing? See, satellite data are available in the digital mode. It has to be processed. When I have the digital data, see, to remove distortions, I said in the beginning, the energy, before it reaches the Earth's surface, it will pass through the atmosphere. There is a mechanism called scattering, and some of the noises will also be incorporated into the image. Because of this backscattered energy also being collected by the sensor in addition to the reflected energy. That means there is a noise, it has to be removed. So to improve the contrast of the image, so that is why we must carry out different kinds of errors must be removed. To remove distortions, they are popularly called as geometric and radiometric distortions in the image. So that is also called as image rectification once, or image restoration or image rectification. then only we have to make use of the satellite data for other applications, like we have to go for image enhancements or we have to go for image classification. Why we have to go for image enhancement? Once it is rectified, the next stage is image enhancement, like contrast stretching. We have to improve the contrast of the image by making use of different techniques. Then piecewise stretching, then we have contrast stretching, then we have band ratioing, principal component analysis, density slicing, edge enhancement, like that IHS transformation, intensity hue saturation transformation, like that. The purpose of going for image enhancement is to extract maximum information from the images, because I am planning to generate a very useful resource map. For that, I must differentiate more number of surface features. So the original raw data will not provide me the required information. So there is a need for image enhancement. That means I'm manipulating the image. So these are represented by digital numbers. When I play systematically with the digital numbers, I will be able to do the manipulation and I will be able to enhance the image, and from which I can extract maximum information from the images. Extraction of information that cannot be displayed, that is statistical parameters. Then automatic generation of thematic maps, that is what it is called as digital classification. Yes, we are going for a supervised and unsupervised classification to measure and define the degree of statistical similarity between scenes. Then statistical analysis, image restoration, radiometric and geometric, just now I said. Then we have to do the image enhancement, radiometric, spatial and spectral enhancement. Then information extraction that are possible through supervised and unsupervised classification. So this is a digital data having regular rows and columns. So left to right, see, these are all rows, and see, top to bottom, they are all columns. So then normally in case of satellite, they are represented, these digital data formats are there: band sequential, band interleaved by line, band interleaved by pixel and all. So normally when they are writing the data to the tape or drive, see, they are following this sequence: band sequential format, band include by line, line 1 band 1, line 1 band 2, like that the things will be written on. So the digital numbers will be represented like that. Then sources of digital image data, normally we are making use of this satellite data. Original satellite data are available in the digital mode, that we can process it, or else we have the scanners, we can convert the analog values. If there is a hard copy, we can convert it into digital mode. Then we have CCD digitizers, video digitizers and all. So we are converting the analog data to the digital data. So to get more information, we are carrying out the enhancement. So this is nothing but it is the process aimed at improving the visual quality of the image so as to make it better interpretable for specific applications. So we have different kinds of image enhancement techniques are available. So with that, we can see band ratio, indices, vegetation indices, NDVI, normalized differential vegetation index. Then we have leaf area index. There are a number of vegetation indices. Then principal component analysis, IHS transformation, contrast stretching, so density slicing and all. See, of course, if you see the raw data here, see, it is not providing that kind of information in the beginning, but here you will be able to differentiate the surface features very clearly. This is after applying the contrast enhancement. So we have improved the contrast. That means, see, because of number of reasons, the satellite sensor has been designed to record the entire dynamic range. Let us say if it is from 0 to 255, it must record 8 bits of data. But because of number of reasons, the satellite data will have the digital number ranging from 30 to 75 only. There is no representation from 0 to 30, 75 to 255. In that case, it is providing very poor contrast. So there is a need to enhance this image by contrast stretching and all. So 30 you bring it to 0 and 75 you make it to 255, then stretch the image so that the information will be available. So more information you will be able to provide by this kind of enhancements and all. The purpose is to get more and more information so that you can easily differentiate the surface features. Then coming to the image classification, so we have the image pre-processing or image restoration or image rectification. Once the images are rectified after applying radiometric and geometric corrections, then we are going for image enhancement so that we will be getting more information. And finally, we have to do for image classification. There are two major categories of image classification techniques which are considered as unsupervised, calculated by software. So it will make, based on the similar reflectance, it will create clusters, and based on that again we have to do the interpretation or classification. Whereas in the case of supervised classification, we are providing the training sets to the computer, and based on that the computer will classify the image into different classes. In case of unsupervised classification, we are going for ISO data and all, iterative self-organizing data analysis system, and how ISO data works and all. Because of the time constraint, I may not be able to discuss these things in detail. But see, this is the output which we have generated for Mangalore Post. This is the image we have generated based on unsupervised classification. Based on the statistics, it has classified the image into different classes. Then we have to go to a particular area, and what are the color assigned, whether it is true or not. We have to do some field checking, and then we have to improve the classification by providing the training set. In case of supervised classification, see, in supervised classification, you select training samples and classify your image based on your chosen samples. Your training samples are key because they will determine which class each pixel inherits in your overall image. So based on that, and here you are providing the training sites to the computer, and based on that it will classify the image into different classes. Of course, this is the supervised classification. In the previous case, it was unsupervised classification, and here we have provided more information in the form of training sites. So this is based on IRS 1D list 3 image. So you can see the supervised classification here. We have number of classes, and see, these are representing different kinds of land use, land cover classes existing in and around Mangalore area. We have the water bodies in the form of rivers. We have the sea, Arabian Sea. We have the Netravati River. We have the Gurup River. Port area is here. Mangalore city is here. So where we have the built up area, where in the built up area again, where I have the residential area, commercial area and all, that kind of classification I will be able to carry out with the supervised classification because I know the area thoroughly, and based on that I am providing the training sites to the computer. Here of course again it is land use and land cover map for the year 2003, and this is for 2013. See, change detection studies can be carried out. The land use land cover means what type of land cover was there about 10 years back, for what purpose that particular land is being used, that is land use. Yes, over a period of time, yes, there is a drastic change in the land use land cover. Agricultural areas got converted into built up areas, and we are going for multi-storied buildings and all. So definitely there is a change. Impervious layers are increasing. So there is a need to monitor these things, land use, land cover changes. We are cutting the forest, we are cutting the vegetation, we are going for concrete buildings and all. Because of this, we are creating impervious layer, infiltration capacity of the soil get reduces. So there is a mechanism called heat island and all that are increasing. So all these things can be monitored with the help of multi-dated satellite data. And these are the figures, statistical figures. Area in 2003. See, we have urban land, agricultural land, barren land, range land, water, and how much area each class occupied in 2003 and 2013. So change detection studies can be carried out, and this type of studies are very much required to monitor the changes. Then comparison of visible and infrared images. See, the same area which are represented in the true color as well as in the false color imagery, but definitely you will appreciate by seeing the near infrared band. This, of course, this is a false color composite wherein vegetation is represented by red color. On either side of the river course, you are seeing very luxurious growth of vegetation. Then here and there you have sparse vegetation, and difference in red will tell you the status of vegetation. So other type of lands can easily be differentiated here in the case of a false color composite, whereas in the true color, see, you may not be able to differentiate the surface features very clearly because here it is vegetation represented by green color, and see, normally vegetation reflects maximum light in the near infrared. That is why normally we must go for near infrared bands for vegetation differentiation. See, by plotting the spectral reflectance curves, we are getting some idea about the spectral characteristics of the Earth surface features, and based on that we can say which are the best bands for vegetation mapping or for soil delineation or water body delineation or for urban related studies, because we must plan before going for any kind of study based on satellite data. I must have the knowledge which are the best wavelength and what kind of spatial resolution, and if it is for repeativity, the temporal resolution to monitor the changes, the flood prone area, inundation, flood prone areas must be mapped, how much area got inundated during the flood time. See, these things must be monitored, or how much area got degraded over a period of time, how much of forest cover removed from 70 to 1990 or 2020. Yes, these things must be monitored. For that, I must go for the temporal resolution. And this is of course a true color imagery. You can see this is of course our Google Earth images, Iconos satellite data, but see, which provides so much of information regarding the vegetation and what type of vegetation may be. If you go for a little bit higher resolution and color composite, with that you will be able to differentiate the vegetation. And there are a number of applications when we talk about a satellite data. Yes, it can be used for meteorological applications like weather forecast, climate studies, global change, hydrology, water balance, energy balance, agrohydrology, and if it is related to soil science, land evaluation, soil mapping, then biology related, nature conservation, vegetation mapping, monitoring, vegetation condition assessment, then forestry, forest inventarization, mapping, then reforestation or deforestation, forest fire detection, environmental related studies, agricultural engineering, physical planning, land surveying and all. Hmm? How many people? 40. See, this is of course a satellite imagery. You can see the entire Western Ghats, Netravati, Gurupur estuary. See, I said in the beginning, which provides you a synoptic coverage. And again, you can see the same area. See, in color composite. See, these are the Western Ghats, Netravati, Gurupur. Then you have the Mulki Pavanje. Then this is Kudremukh area. And we have part of Kodagu district. Then this is Hemavati reservoir. So like that, see, you will be able to demarcate so much of information. See, the straight river courses, wherever you have the coastal plain, what type of, see, suspended sediments, where you have the highest concentration of suspended sediments. It provides you the regional coverage. See, you are getting the synoptic view or bird's eye view, so much of information you can extract. Of course, yes, this is part of Western Ghats and water bodies. See, wherever you have the ridges and Inselberg's residual hillocks, so geomorphological features you can extract based on the analysis of remotely sensed data. And wherever you have the dikes, so normally whenever we go for groundwater prospecting zone mapping and all, you are seeing the ridges and all, they're acting as barriers. In a similar way, wherever you have the fracture zones or the linear features, depressions, any linear or curvilinear feature of geological significance is called as a lineament, and intersection of the lineaments are acting as good groundwater potential zones. And such kind of features you can extract with the help of satellite data through visual and digital image processing techniques. Yes, these are some of the images pertaining to the Western Ghats of Karnataka. And again, you can see the plumes, turbid plumes, which are elongated in the direction of the flow of currents in the near shore areas. This is the Mangalore port area. Then this is Gurupur River. This is the Netravati River. And along the river course, you can see some depositional features, the channel bars, point bars, and other features. See, these in the middle, there is an island, but you can see the periphery, you have some sandy areas, which reflects maximum light, whereas water bodies absorb the radiation. That is how I have to differentiate the surface features. But if it is a digital data, I can definitely say 0 corresponds to the water bodies. And if it is 1 or 2, there may be some sort of suspended sediments may be present in that particular water. So like that, 254 and 255 can be differentiated. 0, 1, 2, 3 can be differentiated. Here I'm getting the absolute digital numbers. So based on that, one can differentiate the earth surface features. Of course, again, this is of different period, Netravati Gurupur, and you can see the depositional features very clearly that reflect maximum light. And of course, this is the satellite imagery in the infrared region of the spectrum. I said each band has its own significance. See, wherever water bodies are there, they look black because they absorb all the electromagnetic radiation. See, from the origin to the river mouth, you can see the Netravati, Netravati River, Gurupu River, Mulki, Pavanje River. Then you have the Udyavara River, you have the Swarna and Sita River, Chakra, Kulluru, Haladi, Maravanti, somewhere here. So you are getting so much of areas information on a single imagery. So this is what it is called as synoptic view. And definitely some of the images are covering half of the state. If you take, for example, NOVA series of satellite, maybe the entire state will be covered in case of geostationary satellites and all. See, that much information you are getting, but they may provide coarse resolution. But for resources mapping and all, we must go for remote sensing satellites where you will be able to see the surface features with the 10 meter, 5 meter, 1 meter and all. See, this is where there is a vented dam. So you can see this is the Tumbe and this is near Sarapadi area. They have constructed two dams across river Netravati and one more dam is here. See, impounding of water. See, this kind of images are very much useful to say how much water is collected along the river course of Netravati. See, water resources related information, vegetation related information I can extract. It depends upon the purpose for which you make use of the satellite data or aerial photographic data. If it is for geology, if he is a geologist, he will extract the geological details. If he is a soil scientist, he will extract the soil information. If it is given to a town planner, he will have different approach. See, like that. So the same satellite images can be used for number of applications. As you can see here, some of the linear features which are oriented in different directions. So just now I said any linear or curvilinear feature. This is near Bandaru area. You can see alignment of vegetation, alignment of topography, alignment of river courses. All this indicates the existence of lineaments. Wherever you see the straight river courses, normally rivers are flowing in a meandering fashion. And if you see, if they are flowing in a straight fashion for a considerable distance, yes, if you see the topography in a linear fashion, the vegetation in a linear fashion, then you can say the area is structurally controlled and you can see series of ridges and valleys. See, this is the upstream of river Netravati. This is near Ettinahole, Sakleshpura area is somewhere here. So you can see these features very clearly on this image. And this is again, this is Hemavati reservoir and you can see some of the lineaments which runs for several kilometers. So there is a major fault here, abrupt ending of the Ghats in a linear fashion. You can see here, it is very clearly visible. See, based on this, we can say where there is a fault and all displacement. Of course, this is that Jodupala area. One of my friend, Dr. Harry, he was in Mines and Geology department. He worked at Madikeri, later he worked at Mysore also. In fact, he too did some work on these areas. So geological related work, groundwater related work, and even on landslides. In fact, we went together to study the landslides of this area. So, but satellite images are providing enormous information when we analyze these images, see color composites and where you have the fallow land, where you have the water bodies, water spread area, how much water is available in a particular reservoir during different seasons. Of course, this is the contour map of Madikeri area based on the digital elevation model. Of course, now satellite images, satellite data are available in the public domain. So number of satellite data, Landsat satellite data are available in the USGS website. Then you can download Landsat satellite data, Aster data, advanced spaceborne thermal emission and reflection radiometer data, shuttle radar topographic machine data. And then you can make use of the softwares available that are also available in the public domain. Make use of the satellite data, make use of the software packages, and definitely you'll be able to generate very useful resource maps. Of course, this is the Talakaveri area where the landslides occurred recently, about 3 months back during the month of August. Yes, 3-4 months back, we have experienced severe landslides, and landslides occurred here. And this hillock came from this place to, there was a movement of this hillock, and this entire house so belongs to a priest, and it got collapsed, and this whatever the mud and all, it got moved to a long distance. And see, this kind of studies prior to the landslide, what was the condition, what has happened after the landslide, yes, that are all possible. And you can see even some of the anthropogenic activities at the hilltop near Talkaveri, Brahmagiri hilly ranges and all. So that is possible with the multi-dated data, and we have number of satellites like NOVA, GO series of satellites, MODIS, Landsat, Spot, Iconos, QuickBird, and added to that we have our own satellites, Indian remote sensing satellites, we have Indian national satellites and all. Of course, this is radio detection and ranging with the microwave remote sensing techniques. Of course, this is LiDAR, light detection and ranging using shorter wavelengths. Then see, we can do some flood damage assessment based on multi-dated satellite data. This is pre-flood 17th July 2006. This is post-flood scenario 9th August 2006. So we have 2 dates of data. How much area got inundated, marooned because of floods? Yes, that kind of maps can be generated prior to the flood, after the flood. Yes, using this satellite data, we can even monitor the forest fire. See, that is possible. And we are having some thermal remote sensing techniques and all, forest fire monitoring, no fire, and this is after the fire and during the time of flood, because sometimes some of the satellites will be passing over an area during the time of the events. So it is possible to capture. So through satellite, you will get the required data. Deforestation over a period of time, especially in Arunachal Pradesh and Assam area. This was based on thematic mapper of 1994, 1999, 2001, so that you can monitor the changes in the forest cover area. Urban heat island, we talk about the urban heat island. See, lot of data are available through thermal remote sensing as well as through optical sensor data. See, we are creating some heat islands. If you compare the heat of the city, that is the center of the city with the suburban area. See, here you have more concrete buildings, multi-storied buildings, impervious layers, asphalt roads and all, concrete roads, asphalt roads, metal roads and all, and you have the concrete buildings. Because of that, these materials absorbs the radiation, electromagnetic radiation. They retain the energy and they will emit back the energy. So in the beginning, I said the satellites are normally recording the reflected as well as the emitted energy of the Earth's surface. Reflected is mainly in the visible and near infrared, whereas the emitted energy is in the thermal region, especially 8 to 14 micrometer range of the spectrum. Earth's surface emits the radiation, and because of that, there is a temperature difference. If you compare the temperature of the urban area, especially heart of the city with the suburban area, because you have more concrete buildings are there, so they absorb the radiation. So they retain the energy and they will emit it back during evening or night hours. Whereas in the surrounding area, you have plenty of vegetation. There is a mechanism called evapotranspiration and all. Because of that, the temperature will be lower there, whereas here the temperature will be higher. So that leads to heat island effect and all. And because of that, you will get a lot of diseases and all. So that can be monitored with the help of thermal sensors as well as visible and near infrared sensors, optical sensors. So NASA has been flying aircraft over 9 cities to determine their thermal characteristics that drive the development of the urban heat island. So based on the color of roofs, more trees, see what are the mitigation strategies at the end. You can suggest some mitigation strategies. So uses of remote sensing, whenever we have the satellite data, it can be used for number of applications, wildfires, then avalanche related studies, landslide related, earthquake, flooding, drought, refugees, volcanic eruption, tsunami, landslides. So for diseases, military operations, see again, this was near Makandur area. You can see the severity of the landslide. Of course, this is a field photo, and you can see along Mangalore Mysore road, you can see on either side of the road there were number of landslides occurred. So during 2018, so this is near Jodupala area. So based on the satellite data, multi-dated satellite data, we can carry out the land cover, what type of land cover is there and for what purpose that particular land is being used. The objective of any classification scheme is to simplify the real world in order to facilitate communication and decision making. So satellite remote sensor data and GIS for land cover, its changes is a key to many diverse applications such as environment, forestry, hydrology, agriculture, and geology. Natural resource management, planning, and monitoring programs depend on accurate information about the land cover in a region. So that is what we are doing, the land use land cover mapping. It is possible with the coarse resolution up to level 1 and level 2, maybe 80 meter, 36.25 meter or 72.5 meter spatial resolution. With that, especially 36.25 meter spatial resolution images are required up to level 2. See, land use land cover classification means if I am in a position to demarcate where I have the urban area, and in the urban area I have the residential area, commercial area, industrial area, transportation, industry. See, these features can be differentiated based on the resolution again. See, I am identifying the urban area, and again inside the urban area, see, Baikampadya area may be having more industries. In a similar way, near the market area, we have more commercial areas. In a similar way, maybe in some of the locations, we have residential area, Car Street and other areas, maybe we have the residential areas. So those areas can be demarcated. See, this is up to level. Again, if I go for level 3, 111, I will be putting that number 111 means 3111 means in the residential area where I have the multi-storied buildings, where I have the single-storied building, and even I can go up to level 4 with very fine resolution. When I say 80 meter, it is coarse resolution, 72.5 meter. Now satellite images are available with 30 meter, 20 meter, 5.8 meter, 4 meter, 1 meter, less than a meter. With less than a meter resolution, definitely I will be able to go up to level 4. So that is possible. So again, we can generate the maps, state level, national level, international level maps and all can be generated. This is how the built up area and the description of land use land cover classes. So this is how you have to assign the numbers. 1 means built up area, 2 means agricultural area, 3 means wasteland, like that. So you can see various types of land use land covers. This is thermal infrared remote sensing. Especially here we are measuring the thermally emitted radiation. Yes, over a period of time, significant changes have occurred. So vegetation cover got removed and you have more built up area so that you can monitor what was the condition then and what is the present scenario. So you can compare the land use land cover map with the land surface temperature. So you will come to know whether there is an increase in the temperature or not. So these kind of studies can be carried out with the help of thermal remote sensing. Forest fires can be detected, and even if any industry is discharging the effluents to the nearby stream, yes, that can be studied through thermal remote sensing. So kinetic versus radiant temperature and all. And in the case of radar, it is having the penetration capability. Yes, it is penetrating through the clouds, irrespective of the weather. Day and night imaging capabilities are there for this type of satellites. So you can collect the required information through this type of satellites. That is called as microwave remote sensing, wherein the energy, longer wavelengths are being used, especially when we talk about the planetary geosciences or planetary related studies, outer planets. We have sent satellite to Mars, we have sent satellite to Moon and all. To know more about the Moon's geology or Mars geology, we need this kind of sensors, especially microwave remote sensing technology we must make use of, because longer wavelengths can penetrate, the shorter wavelengths cannot reach sometimes. So in that sense, yes, we need this type of remote sensing technology. So especially the microwave remote sensing technology, which are having all weather capability, day and night operation, no effects of atmospheric constituents, sensitivity to dielectric properties, especially water content, biomass, then sensitivity to surface roughness. Then there are a number of other applications when we talk about microwave remote sensing. So there is a term called synthetic aperture radar. We have real aperture radar and synthetic aperture radar. See, we cannot make use of the longer antenna physically, but here it synthesizes. So the antenna size is synthesized. So based on that, see, they are making use of this synthetic aperture radar images so that you can generate a digital elevation model of the area. So from which you can extract the flow movement and flow direction and all can be determined. SAR interferometry for subsidence monitoring. Yes, if there is a subsidence or even there is a rise of the land, Himalayas are rising, we say, that can be monitored to the centimeter accuracy. Then SAR for synthetic aperture radar for soil moisture, then biomass estimation, crop estimation, flood control, oil spill monitoring and all. So with that, see, we can make use of this SAR synthetic aperture radar for number of applications. So now coming to the other outer planets, see, we have sent a satellite to Moon. That program was called Chandrayaan-1, and recently we launched one more satellite called Chandrayaan-2, and now we have sent satellite to Mars also. In the first attempt, none of the other countries have succeeded in sending a satellite to Mars in the first attempt. Mars orbiter mission it is called as. So we sent a satellite to know more about the geology of that area, what are the minerals present, whether water is present on that planet. So all these studies can be carried out. There are a number of payloads. So we have the spectroscopy. We are going for hyperspectral remote sensing, wherein the mineral concentration, different types of mineral assemblages can be studied with the hyperspectral remote sensing with the different kinds of sensors. So again, Chandrayaan-1, then impactor probe and all. The spacecraft carried 11 scientific instruments, payloads built in India, USA, UK, Chandrayaan-1, Germany, Sweden, and Bulgaria. So it provided enormous information. So these were the terrain mapping camera, TMC, hyperspectral imager, then lunar laser ranging instrument, high energy X-ray spectrometer, moon impact probe, MIP, X-ray spectrometer, near infrared spectrometer, like that, to know more about the moon's geology, mineralogy, and water content, and some other aspects. They have sent this satellite. Even the rare earth minerals are available there. They are playing a significant role. So Chandrayaan-1 mission objectives. See, these are some of the studies, especially carried out by some international scientists, and they have published number of papers in the highly reputed journals. So Chandrayaan-2 and all, you can see the latest satellite we launched during 2019. The first satellite was launched during 2008, and after 11 years we launched Chandrayaan-2. So basic information, see what kind of information we can, because we cannot study these things. So we have to make use of the microwave technology, hyperspectral remote sensing technology, and all, to know more about the moon. So these are Chandrayaan-2 objectives: to pursue lunar scientific studies, water identification, mapping of surface composition, explore in situ lunar regolith. See, a lot of data are available through satellites now. So we have to make use of this satellite data meaningfully, so that maximum information can be extracted. Maybe computer science people, I think, if they are in a position to explore these possibilities, yes, if they provide the enhanced images to us by classifying the images, yes, we, the application oriented scientists, can, yeah, do the interpretation in a meaningful manner, and we can, yes, generate different kinds of thematic maps. So these are some of the specifications of Chandrayaan-2 and all. So you can see even the craters, impact craters and all. But on the surface, we cannot study the impact craters so clearly because of weathering, plate tectonics and all. Most of the crater areas are disintegrated, or they got removed over a period of time because of these geological processes, because of natural processes and all, whereas they are intact on the moon as well as on the Mars. So we can study those features very clearly through remote sensing techniques. So a lot of data are available, and you can see Venus and Mars. Now we have sent a satellite to Mars also, Mars orbiter mission. Only the difference is carbon dioxide concentration is more in case of Mars, whereas here we have nitrogen and oxygen are the major elements. See, but shield volcanoes are common on Mars surface. So you can see the basaltic magma and all. So it is almost resembling similar to that of the Earth in several respects, as well as in several aspects. So these are some of the specifications: atmosphere of Mars. So these were again studied through satellites. So Olympus. So this is again Mars. This is a crater. So different kinds of craters you can see on moon surface. So some of the data are available now, especially for Mars as well as for moon. So there is a need to explore this. So geologists, yeah, they can do a lot of mapping, but again, the data are available in the digital mode. Only computer science people, yes. And if they combine geologists and computer experts, they can do a lot of work by using this satellite data. Enormous data are available in the optical region of the spectrum, thermal region of the spectrum, microwave region of the spectrum, hyperspectral data are available. There is a need to explore all these. how best we can make use of our knowledge to extract meaningful information from these images. So polar ice caps and all, north polar ice cap, frozen seawater on top of frozen water. So the atmosphere of Mars. So this is nothing but, see, again you can see the topography of the Mars. See how the Mars topography looks like, and also that you can see these are the references. And with this I will end my lecture. So again, I wish to thank the organizers, especially Dr. Sharmila Madam, Professor Sharmila, Head Computer Science Department, for giving me an opportunity to share some of my thoughts. So I am very much thankful to Professor Sharmila Madam. So I think this is one of the best technique tool available, and with the help of, see, application oriented scientists and computer experts, if they sit together, I think definitely, because I said again, I am repeating once again, we are getting enormous data through satellites, because we can explore the outer planets only through this technology. We have the optical sensor data, we have thermal sensor data, microwave data, hyperspectral, laser technology and all these data are available in the digital mode. There is a need to explore maximum information we must extract, and we have to generate the thematic map so that we will be able to get more and more information about the outer planets, about our own planet. But definitely, if we sit together, maybe computer experts as well as geologists or geomorphologists or geographers, definitely, or the decision makers, definitely we will be able to extract maximum information from the remotely sensed data. That is what I have explained so far. The satellites used for natural resources mapping, disaster monitoring, say urban related studies, urban heat island, then natural disasters like landslides and all, flood inundation mapping, and all can be carried out. We are getting enormous data. See, we have constellation of satellites. Every day, one or the other satellite will be passing over your area. So you can monitor the dynamic changes. The land use, land cover related studies can be carried out, and geological related information, mineral resources of an area, water resources of an area can be carried out. There is a need to go for image enhancements and all, image classification in a better way, maybe machine learning or whatever. I do not know much about, maybe madam has to tell something about this machine learning and all, but we are normally using user friendly software packages, the supervised classification, unsupervised classification. Then we are carrying out different kinds of image enhancements on the digital data. We have ERDAS imaging software available comprising of different functions. We can import, export the satellite data. We can carry out different kinds of enhancement like IHS, intensity, hue, saturation, principal component analysis, density slicing, band ratioing. At the end, we are getting some useful output, and that we are making use of to generate the thematic maps. Yes, now there is a need to explore this, maybe more and more computer programming or more and more machine learning. See, different kinds of programs are available. Yes, definitely we can extract maximum information from the images, and that can be used for the benefit of the society. With this, I will conclude my lecture. Again, I am thanking Professor Sharmila Madam for giving me an opportunity to share some of my thoughts. If there is any question answer sessions, I will be able to answer some of the queries. Madam, thank you, Madam, for again.
Thank you very much, sir.
Again, I am thanking the Pace College, Engineering College authorities for giving me an opportunity to share some of my thoughts. Again, I am repeating, this is one of the best technology for engineering people. Definitely, you have to explore, not only for civil engineering applications. We geologists are making use of this to the maximum extent. Botanists can make use of forest resources mapping, and definitely engineering faculty can make use of this. You can go for different kinds of projects. ISRO is funding under response scheme. There are a number of funding agencies. Definitely, you can ask for some funds so that you can carry out the work. With this, I will conclude. Again, I am thanking Professor Sharmila Madam. Thank you, Madam.
Thank you, sir. Sir, we have a
And
question.
special thanks to Ankita Madam also, since she introduced me to the audience. Thank you, Madam.
Thank you, sir. Sir, we have a question here.
Okay.
What are the available data sets of hyperspectral document images for research?
Yes, there are a number of satellites dedicated for different kinds of applications, not only our Indian satellites, even I said, see, we have some sensors available, especially they have launched a few sensors, hyperspectral sensor to know more about Moon and Mars. So to delineate the lithological units, mineral exploration, vegetation mapping, yes, we have some of the satellites available. Indian remote sensing satellite data are available, and at the same time, some foreign countries' satellite data are available in the public domain. Yes, hyperspectral data are available with hundreds of spectral bands, very, very narrow bands, and they're contiguous bands. They're having more advantages. So definitely you can make use of the satellite data, or you can approach NASA of USA, National Aeronautics and Space Administration of USA. They have a lot of satellite data. European Space Agency is there. Indian Remote Sensing Agency, that is National Remote Sensing Service Centers are there. If you request them, they will provide the required satellite data, and you can process it. There are different kinds of software packages are available. You have to make use of that. And definitely hyperspectral will provide more information than the optical, but at the same time, optical sensors are providing very fine resolution images, whereas in the case of hyperspectral, we are giving more weightage to the spectral resolution rather than the spatial resolution. Yes, it is possible, and they're available. The data are available. Maybe you can contact me. The person who asked that question can contact me, and I will provide the required information.
Yes, sir. Thank you, sir.
No. Thank you.
So here we come to the end of day 4 session. I, Professor Ankita, on behalf of Department of Computer Science, PA College of Engineering, take it as my privilege to extend a heartfelt gratitude to Dr. H. Gangadhar Bhatt, Professor, Department of Geoinformatics, Mangalore University, for the excellent session. I'm sure the fine-grained concept followed by an excellent hands-on session would have given all the participants a complete exposure in materializing and understanding even the highly complicated topics in a very simplest way. I affirm that the participants will have a lot of takeaway from this highly knowledgeable session and help have an exponential leap in their research progress. Thank you for such a wonderful and highly informative session, plus for the patience and earnest attempt to reach every enthusiastic minds. Thank you, sir. Dear participants, thank you for your active participation throughout the day. Before leaving the meeting room, I request all the participants to give the feedback of today's sessions. We shall be back tomorrow morning at sharp 10 with a fresh mind to absorb new concepts. Links for the materials that are shared by our speakers will be shared to all the participants as we receive it. Thank you, one and all.
Thank you, Professor Sharmil and Professor Ankita, madam.
Thank you, sir.
Thank you.
Ini dengan kerja ni, saya lanjut